So today we're going to continue from where we were last time, talking about the benefits of scaling, which is what MEMS is all about. Just a couple announcements. We talked about this last time, and we got this changed last time, but it's on the web. It's also reflected in the new course information sheet that's on the web, and that's that Henry Barrow's office hours have gone from Tuesdays 10:30 to 12 to Tuesdays 10 to 11:30 to accommodate those who have classes on both Tuesdays and Thursdays. Brian Pepin's office hours will remain where they were, 10:30 to 12. Okay. The notes from last time, I don't know if you checked, they're online. The webcast is also up and running, so you can even watch that on webcast. So everything is working. I should also mention that if you looked at for the notes online, you'll also see modules that are online. These are things that you can download and look at before the lectures. They give you a good snapshot of what I'm going to talk about during the lecture. And actually, I'm going to go through Module 2 today to some extent with some amount of writing as well at the same time. Okay? And so that's what we're going to do, start going through Module 2. But before I start, are there any logistics that we need to take care of? Did you all go to discussion section yesterday? Or some of you go to discussion section? Okay. I guess one more thing I should mention is that your homework number 1 is online as well. And so for your homeworks, I'm not going to pass out actual paper copies of these during lecture. I'm going to let you download it from the online website. And I guess I can try to get on the website. No, I can't, because I'm not actually on this. Well, anyway, you'll see the homework yourself. It's not substantial. It's basically reviewing, not even reviewing. It's asking you to look up some MEMS type devices, data sheets or so, just to familiarize yourself with the types of devices we're working on. It doesn't include a whole lot of strenuous analytical activity except for the last problem on it. This homework is assigned today, but it's going to be due in 2 weeks. Okay, so it's not like it's an emergency to start on this. All right, okay, so let's get started, and let me start with the module. And so this is the module. This is exactly what you'll find online, except you'll find the PDF version of this online. And again, if you like having this copy in your hands, you can take notes right on this. That's what the module is for. Otherwise, do with it what you want. Let me go into this mode here. We actually started going into this a little bit last time. And so we started talking about the benefits of miniaturization. We talked about this, which is sort of giving examples of how miniaturizing in the mechanical domain give you all sorts of performance enhancements. And you can see all of these performance enhancements right here. And then we started talking about vibrating RF MEMS, which is just one subset of MEMS. And a subset that's making an impact in the market today in the form of oscillators and eventually in the form of things that make your cell phones work. In fact, they're already in your cell phone. So F-bars, if you know what those are already in your cell phone. So it's a MEMS component that really makes your cell phone work the way that it's working even today. We talked about this concept, sort of a very simple description of what vibrating RF MEMS is. It's in some ways as simple as scaling of guitar strings, where we looked at a guitar string where if you had a guitar string tuned to an A and you pluck it, it's going to vibrate at 110 hertz. And that's what you hear with your ears as an A. Depending on how good the guitar string is, if it's dirty, if it's not, it can very sharply vibrate at that 110 hertz, or it can vibrate in such a way that it lets in other frequencies as well. And that's the difference between a high Q and a low Q type frequency selecting circuit. And so it's a mechanical device, but I'm already calling it a circuit. And as you'll see, it really is just a circuit element that we're going to be able to use to build much larger circuits of mechanical components. This 110 hertz we mentioned last time was too low a frequency for wireless communication. So you might know that your cell phone operates usually in the gigahertz range, some of them in 900 megahertz, but most of them between 900 megahertz and 2.4 gigahertz. And you need a device that can do something like what this is showing here. It can select a certain frequency and reject all other frequencies, because that in the end is what your cell phone is doing as well. It's basically trying to receive a very specific frequency, which you're communicating with someone else on. But then there's, of course, many other conversations happening at the same time, and those other conversations are happening at different frequencies. And so what you need to do is reject those frequencies where the other conversations are happening and collect only yours. And that's why you need to have these tuned frequency circuits like this. To get to the higher frequencies that cell phones require, you could just take a look at a very simple physics for any mechanical resonator. So any mechanical device, period, will resonate. It's going to have some frequency at which, when you excite it at that frequency, it's going to move in a big way. Right? Even bridges have this. You may remember the Seattle Bridge, right, when they had an earthquake or a tremor or so, and the motions caused by the earth were at exactly the right resonance frequency for that bridge, right? This is a big concrete bridge. Right? You don't think of a big concrete bridge vibrating like a guitar string, but it did. In Seattle, that bridge went like a guitar string with huge amplitudes or so, and that's just because the energy going in was at the very frequency, that's its resonance frequency, that allows it to vibrate in a very large amplitude. That's what's happening with guitar strings, right? If you hit it with exactly that frequency, or you pluck it and you let it go, it's going to remain at that frequency right there with the large amplitude. It's only going to take on that frequency. That frequency is determined by the stiffness of the mechanical system divided by its mass. Okay, so if you think of this equation, and very quickly you could see that if you could take that mass and lower it to very small values, you can drive this frequency up to very large values, and perhaps up to the gigahertz range if you make it small enough. And so just an example of making this guitar string smaller using MEMS technology is right here. So this is an example of a MEMS-based guitar string. It's sort of anchored at these ends here. This is the string, but it's not really a string, as you can see. It's more like a beam, because it has a finite thickness, finite width. So does the string, but the thickness and width of the string is much, much smaller than the length. In this case, the length is about 80 microns long. The width is 8 microns wide, and the thickness is 2 microns thick. Okay, so we're working in dimensions of microns, which is sort of characteristic of MEMS technology. There are some nanoscale features in this as well, and that is that the gap between this electrode, which is actually not touching the beam. So this electrode is actually about 100 nanometers underneath this beam, and there's a space of 100 nanometers between the electrode and the bottom of the beam. And what this is for is you can apply an electric signal to this, a voltage, that will create an electric field between the beam and the electrode. And then you can vary that voltage at the resonance frequency of this beam. And if you do that, you're going to get the beam to vibrate. Okay, so by varying that voltage, you're varying the electrostatic force that's being applied to the beam at that frequency. Since the beam is seeing a force at the frequency of its resonance, it's going to move at a very large amplitude. If you try driving it at a frequency not at resonance, it's not going to do much. It may move a little bit, very tiny amplitude. But at resonance, it starts really moving. Okay? Again, all mechanical systems will do this. This is a plot of the vibration amplitude versus the frequency of excitation, where you can see clearly that this beam with those dimensions is at 8.5 megahertz. That's a lot higher than 110 hertz. That is not a gigahertz yet. Okay, so we'll talk about how to get to gigahertz in a few slides from now. But just a few interesting things about this beam here. So one, we shrunk this beam to get to high frequencies. But what are some of the consequences of making this beam too small? Well, you can see the consequence right here, and that's this concept of quality factor. So quality factor is sort of a measure of how sharp the spectrum is, how selective, how well you can select a certain frequency. And you can see that if you operate this beam in vacuum, you get to a very high quality factor on the order of 8,000. Okay, that's a lot higher than guitar strings will get. So guitar strings, right, a really clean, good guitar string could get a Q on the order of 700 or something like that. 700 to 1,000. A dirty guitar string may shrink down to 100 or something. To compare this to transistor circuits, we talked about this last time. So if you're using integrated circuit transistors and you're designing using analog circuits, What do you have that can create resonators? You have capacitors, which actually are quite high Q devices on chips. So capacitors can have Qs on the order of 10,000 or so, if you've got good ones in an integrated circuit technology. The problem with integrated circuits is you don't get good inductors. To make a resonant circuit, you need both a capacitor and an inductor. And the inductor in a typical integrated circuit technology is going to have a Q on the order of 5, 10 if you're lucky. Okay, so that's what you're looking at. You're looking at the difference in ICs of Qs from 5 to 10 versus mechanics where your Qs are normally in the thousands. Okay, sometimes hundreds of thousands. Is that a question?
Why are inductors such poor?
It all happens to do, so Q is defined as energy. So the question for those on the web is why do inductors have such poor Q? So it has to do with the reactance you can generate in a certain element versus the loss. And so again, Q quality factor is energy per cycle. So think of something vibrating. Okay, it's got a certain amount of energy while it's vibrating, divided by the energy lost per cycle. Okay, and the energy losses come about in a mechanical system. The losses can come about because the anchors are radiating energy into the substrate. For this thing, it's going to be air damping, thing that I'm showing right here to get that 50. I'll talk about that in just a second. For inductors, the problem is that the energy is sort of proportional to omega, the frequency, times the inductance. Okay, so the reactance gives you sort of what the energy is. You got to divide that by the losses, which are determined by the resistance in the system. And so an inductor is a long, right, spiral of conductor. That's a lot of resistance in the end. And the omega L that you can generate is not that much bigger than the R that you have. Okay, so that's just electrical. In an electrical system, that's what you have. In a mechanical system, the difference is it's no longer omega L, it's omega times M. Okay, so omega, which is frequency, times mass, where mass is the equivalent quantity in mechanics to inductance in one of the analogies. And you'll learn about this in great detail later on in the course. Okay, so you get a certain omega times M, but then the dissipation in mechanics is extremely small. So omega times M divided by the dissipation, which is damping, can be an enormous number in mechanics, whereas in electronics, it's not that big. Okay, so there's a difference between those, and you can sort of see, if you're a circuit designer, the big advantage to go into mechanics if you have a technology that makes available mechanical systems to you for at least circuits that want to do this, that want to select frequencies. And I just described to you that that's a huge range of circuits, right? All of your wireless devices, that's what they're doing. Okay, our whole wireless age is basically just selecting certain frequencies. Okay, there's a lot more to that, right? There's modulation and everything, but in principle, if you could not select a frequency versus others, you'd have a very difficult time doing wireless communication where many people can communicate at once. Okay? So going back to this device here, talking about losses, I mentioned that you could have a Q of 8,000 in vacuum, which is a very useful Q. You could do a lot of things with a Q that much on chip. But when you operate this in air, so you take away the vacuum and you let this operate where we are right now, the Q drops to about 50. Okay, that's considerably higher than what you can get in electronics. Okay, but it's still nowhere near as good as it could be. So the question is, why did it drop to 50? Well, this has to do with some of the consequences of making something small. So we benefited from making this small in that the frequency rose an enormous amount, okay, by several orders of magnitude, from 110 hertz to 8.5 megahertz. Okay? But we suffer a bit because now the device is so small and it has so little energy per cycle. Okay, so very little energy per cycle, but it's losing even less energy per cycle. That's why its Q is still high. But it's got so little energy per cycle that if you ask it to push air molecules around, it has to expend a significant fraction of that energy just to push those molecules around. Okay, it's like you and I trying to move in a swimming pool. Right? It's difficult to do. You expend a lot of energy, and because of that, the Q drops to about 50 in air. Okay? So that's a minus to the technology. That's the con. How do you solve this? Well, one way to solve it is to make sure that you have a technology where you can encapsulate this in vacuum. Okay, the problem is vacuum encapsulation costs money, and you may not want to do that. Turns out there's another better way to solve this problem where you can actually get Qs of 10,000 in air, but we'll talk about that a little later on. Right now, though, I want to spend a little bit of time on this topic here just to go through some types of things that you either know or you'll learn in this class very soon. And that is sort of derive the expression for frequency for this guitar string first and then for the beam afterwards, just to give you a little practice in doing this. Whoops. All right, so let's talk about scaling of guitar strings. Can you guys see that easily? Does that writing look a little scrunched? It does? Scrunch in the horizontal direction? Okay. All right. Now, the reason why it's scrunched is because my screen is on widescreen while this is not. And so I could take some time to try to change my screen to what it needs to be. I just reinstalled a new hard drive on this. And so this is not set up correctly on this. But hopefully you can work with this, because me installing this, you don't want to spend the time doing that. I'll do it for the next lecture, but this is going to look a little bit scrunched as I write this. Okay, so first of all, what is a guitar string? I think you know, right? But we're going to equate it to a more technical terms. This is a transversely vibrating stretched wire. If you're having trouble reading that, that's partially probably my handwriting too. Okay, so for a guitar string, we have a stretched wire, say like so. Okay, but in a lot of mechanical problems, you have to worry about what kind of boundary conditions you have. And so there's all sorts of different boundary conditions in mechanics. There's fixed-fixed or clamp-clamp. There's simple supports. A guitar string is using a simple boundary condition, which is sort of drawn often by these little pivot triangles here. And so what this is saying is that this boundary condition is such that the motion in the z direction, and so if I come out here and I say this is the z direction, and let's call this the x direction, okay, on this, so I guess I will have a axes that look like this. Okay, so in this boundary condition, the motion of the z direction for simple support, which is what this boundary condition is called, z at x equals 0, and so let me draw in the x-axis here. At 0, and this is x equals L. So z at x equals 0 is equal to 0. Okay? So that's one of the conditions of this simple support. But you'll notice that I'm not really constraining this beam too many other, or this string too many other ways. So this string, as it starts vibrating here, and so let me show a little bit of vibration. So it vibrates, it's going to take on a mode shape that might look like that. As it vibrates, I'm not constraining the angle, for example, that this makes with the support. Right? That's an unconstrained thing. So that's part of the properties of a simple support as well. We'll go a lot deeper into supports later on in the class. And a lot of the stuff that I'm going to do here right now, we're going to do in a lot more detail later on. This is just a first pass through this. And so I'm not even going to try to teach you a lot of the elements of this. I'm just showing you stuff that you may have seen before. If you're in ME, you've seen this before. If you're in EE, you probably have too in some physics course long, long ago that you may not remember. Okay, but this will all come back later on as well, because I'll go into much more detail into this. But the simple support gives us that boundary condition. On the other side, of course, just through my drawing, we also have another simple support. Where I have the same boundary condition. And both of these things are boundary conditions. So I guess I'll just abbreviate that by BC on boundary conditions. Okay, so what are we interested in with this problem here? First of all, let me just be complete here. So the dashed line is often what we'll call the mode shape for a vibrating type, beam or string in this case. And so what we're most interested in finding here is an equation for the resonance frequency. And I guess we're going to be most interested in the fundamental mode. But as it turns out, we're going to derive an expression for all the different modes as well, since it's easy to do with this guitar string. And so how do we go about doing this? So one thing that you may have worked with in the past is a free body diagram. And this is a consequence of my not having this computer set up correctly. Because when I get close to the edge of this thing, the dot no longer lines up for some reason. The edges on this pull things out to the left. Okay. All right, so we want to make a free body diagram for this. And so we kind of already have a picture for this. And so in making a free body diagram, what I'm really trying to do is write down a condition for the dynamic equilibrium of this moving, vibrating string. Okay, so I don't want to work with the whole string at first. What I want to do is grab a small piece of it. And that small piece is going to give me all the different physical constraints on this that define a differential equation that then will determine for me what the frequency is for this. Okay, so I'm going to grab a piece of this. And let me grab, say, a piece right here. And blow this out into my free body diagram down here. So here's where I'm going to keep that thing up on this side. And come down here. Okay, so for here, I'm going to draw this little section here as this. So that's a tiny piece of that section. And on this section, it's a guitar string, so it's going to be under tension. Also, even if I just pull it down the way that it is, it's going to be under tension. And so I can model those tension forces by forces along the axis of this little differential element of that beam. And so those will be equal tension forces S on either side. Okay, so that's a tension. Now it's and all the tension is an axial force here. Okay, that's pulling on this beam, pulling it taut, or on this string, pulling it taut. Okay, and so those are two of my forces. And you know that I'm going to have to create a balance equation that includes those forces. Right? But those aren't the only forces that I have in this system. And one of the forces that I have is an inertial force. Right? The fact that this beam is moving means it's got an inertia. Right? An inertial force is equal to, from your physics courses, mass times acceleration. Okay? So I need to get an equation for mass, and I need to get an equation for acceleration here. And so let me take this as a direction for my inertial force. And I can write down an expression for inertial force as m prime, which is a mass per unit length. And if I'm going to express that in terms of unit length, then I'm going to want to multiply that by the unit length of this thing, which is dx. So over here, let me just be clear that I'm looking at an element that's at some point x here. So that distance is x here, and I'm looking at an element that is of length dx. Okay? So the length of this element I'm looking at right down here is dx. And so m prime times dx is the mass of this element, since m prime is a mass per unit length. And then I have to multiply this by acceleration, which in this case is just the second derivative of z, since that's the direction that it's moving with respect to time. Okay? So that right there is my inertial force. Which is mass times acceleration. Okay? And so I've got that force going in the downward direction. What I need to do to create a balance of force equations is find the forces due to these tensions that are also going in the vertical direction. Okay? And so to do that, I need to know these angles here, right? Because I've got a vector of force that's going along whatever direction this element is, but now I need to convert the direction of that force to the vertical direction. And so I'm going to go ahead and there's my vertical line right here. I'm really looking for this force that's going in that direction. Okay, so I need to know this angle right here, and this angle right there is just going to be given by theta, of course, but theta is about equal to the tangent of theta when theta is very small. So I can express that angle, or at least the tangent of theta, as dz dx, and then the force component right here becomes s times dz dx. Okay? And I can do the same thing on the other side. So I'm looking at this. I want the force going up in that direction, and the force going up in that direction is going to be this s times whatever that angle is. But now that angle is a little bit different. Right? That angle is going to be the angle that I had on this side, but modified by any angular change that occurred across this differential element. And I can model that by on the left side, it was dz dx, but now I'm going to model that by the second derivative of z with respect to x times the length of that differential element dx. Okay? And so now I've got all my forces in the vertical direction, and I can write an expression for the condition for dynamic equilibrium. Which is all of these forces together. So s times this dz dx, where I'll take all upward forces as positive, all downward forces as negative. So this is going to be plus second derivative of z with respect to x times dx, and then minus the other force component, s times dz dx, minus the inertial force, m prime times dx, times second derivative of z with respect to t, and all those have to be equal to 0 if I have dynamic equilibrium. Okay? So I have this equation, and this is a type of equation that you have solved before. I think whether you're an EE, whether you're an ME, certainly MEs, I believe, have solved this exact equation. People tell me that's not true who've taken the course before who are MEs. I have a hard time believing that, but EEs have certainly also solved this because this is the same equation, differential equation you get for a lot of EM type problems, electromagnetism type problems, okay? And so I'm not going to solve this for you. I'll leave that up to you, but it's a very simple solution. If you solve this, you can come up with a frequency equation associated to this where you could solve that to finally get an equation for the resonance frequency, which looks like this for this particular problem. So that's F sub I is equal to I divided by 2 times L, where L again is the length of this beam, as you can see from this axis on the right side there. And then this times the square root of S, that tension force, divided by the mass per unit area. Okay, so that then becomes the frequency equation. And immediately you can look at this equation and see that it depends on length. And how does it depend on length? If I reduce length, so just from a scaling argument, if I take L and I reduce it, which is what L arrow down means, then the frequency goes up, which is exactly sort of what we've been predicting. You scale something, you make it smaller, it goes fast. So people who are EEs know this very, very well in an indirect way, because if you take a transistor, you make it smaller, it is going faster. Okay, but this is a universal thing. It's not just transistors where this happens. It happens in mechanics, it'll happen in chemistry, it happens in thermal problems, everywhere. You make something smaller, it's going to go faster. Okay, and so that's one thing that this technology allows us to do. It allows us to access speeds that without being able to shrink things, we would not have access to. Okay? One thing I should mention here that I basically is the mode, right? So plug in either 1, 2, 3, 4, first mode, second mode, third mode, and those are all the different frequencies this guitar string will vibrate at. Okay? All right, so this is a guitar string here. So what we're more interested, though, is this MEMS type device here, which in fact is not a guitar string. All right, so what I'm going to do is I'm going to pull out this thing here, steal it from another place in this, and just stuff it right here. And this is a different beast here. This is not exactly the same thing as a guitar string. Let me put this on that side. This is a clamp beam. Okay, so it's fixed on both ends here. It differs from the guitar string we just looked at in that, one, it's not a string, it's a beam. Okay, two, it doesn't have simple supports on both sides. It has fixed supports or clamp supports. And so what do I mean by that? If I were to make a schematic of this beam, I could draw the beam itself. That's going to have a certain finite thickness, of course. And the boundary condition, instead of those little triangles, I'm going to make that the boundary condition. Okay, so this is a different boundary condition because what it's doing is it's actually enforcing that that angle remains 90 degrees at both those ends. Okay, so when this beam actually contorts to vibrate, what it's really doing is keeping its 90 degrees at those ends and just contorting like this. Okay, so deriving the frequency equation for this is the subject of a point much later in this course, so I'm not going to do it right here and now. But let me just be complete about this right now. Let me call these things clamped, or sometimes we'll call them fixed boundary conditions. Those on both sides. Let me label a couple things on this too, because I'm about to write an equation for this. We'll still call the length of this thing L. So that's still L. And we'll call the thickness of this thing H for height. And so at this point, because I'm not going to derive the equation for resonance, I'm just going to write it for you. We're just going to take a look at its dependencies here. Okay, so the equation for resonance is simply F naught. So I'm first going to write, it really derives from this. F naught is 1 over 2 pi times the square root of the stiffness divided by mass. That's an equation that I showed you before in one of those slides. But when you do the whole differential analysis of dynamic equilibrium for this, which is considerably more involved than for that string that we just did, this ends up being equal to 1.03 okay, which is the number you get out of that full analysis. I won't tell you exactly where that number comes from here yet, times square root of Young's modulus. Well, let me not say what these are yet. So square root of a quantity E divided by rho times the thickness H divided by L squared, okay, where in this expression E is the Young's modulus of elasticity. This is really just a material property that has been measured in the past and tabulated in many different books. Usually that's given in dimensions of gigapascals, okay, which is the SI unit for this. Rho is the density, okay, which is the SI unit is kilograms per meters cubed. And the other things were sort of designed in the picture, but for completeness, I will write them down. So H is thickness, L is the length of the beam, and both of these are in meters. Okay, so that's the frequency equation for this clamp beam that is an actual fabricated beam for you. And so we could take an example and really just plug in the dimensions that I said this beam was fabricated with. And so I said the length of it was 40 micrometers, so it's 10 to the minus 6 meters. The thickness was 2 microns, and the material that this was made of is polycrystalline silicon, okay, which I'll abbreviate polysilicon, or sometimes people will even just call it poly, assuming that it's silicon. At least a lot of CMOS people will do that. You can't really do that in MEMS because there's lots of polys. It could be diamond, silicon, silicon germanium, all sorts of different things. So polysilicon here. Young's modulus of polysilicon is on the order of 150 gigapascals, and that will change a little bit depending on how you deposit the polysilicon. But in most cases, at least here at UC Berkeley, 150 gigapascals works very well. The density of polysilicon, 2,300 kilograms per meters cubed. And therefore, if you just plug all of this into this expression, take my 1.03 times 150 giga, and so you're encountering my shorthand notations here. When I want to say giga, which is 10 to the 9th, I'll write a capital G, divided by 2,300. Times 2 microns, and so I'll just use the mu sign for microns when I do these things, divided by 40 microns squared. This ends up being a frequency F naught of 10.4 megahertz. Okay, so that's our frequency equation. Now what was the yes?
The width doesn't matter? The width of the beam?
Yeah, the first order, the width is not going to matter for this, but the second order it does. Okay, so it all depends on how accurate I want to be about determining this. And so there's a couple other things that I should mention, right? When we looked at the actual data for this beam, which maybe I can bring it up here, right? This is vibrating not at 10.4 megahertz, right? This is vibrating at 8.5 megahertz. Okay, so what's the deal? Why is this thing vibrating that way at a different frequency? Well, there's a lot more things going on than just our ideal beam. So this is our drawing of the beam. This is what was analyzed to get the equation that I just wrote for you. First of all, there are width effects, like you were saying, but the width effects for this beam are not going to be that consequential because the beam, 40 microns long versus 8 microns wide, that's quite a bit longer than the width, right? When you shrink it down to 10 microns long and it's 8 microns wide, then you start having to worry about certain other effects, Poisson effects and that sort of thing. But that's not the case here. But if you look at this beam, and this is the consequence of how we make this. Okay, this is made using that technology we briefly described last time, which we'll go into great detail later on. But you'll see one consequence of that technology. You don't have a nice straight beam here. You actually have a beam that comes up over its anchor condition. And the anchor condition, first of all, is not exactly this. It can't hold it exactly to 90 degrees. Second, you can see that this beam has some ups and downs there. And these ups and downs shadow the electrodes. So that's part of the process technology. In the process technology, we put these electrodes down first. Okay, and we didn't planarize the surface after we put down this structural film. So this structural film takes on these little glitches here. And you'll find that these little glitches will also knock the frequency down from 10.4 megahertz. Okay, but it won't knock it all the way down to 8.5 megahertz. Okay, something else is actually knocking it down to 8.5 megahertz, and that is much deeper in the class. That's the fact that we are driving this with a voltage here. And part of the voltage we drive this with is where we put actual a DC bias voltage and an AC voltage on top of it, where the AC voltage is supplying the actual force that drives it, but the DC voltage sort of amplifies that force. But the other thing the DC voltage does is it creates a parasitic electrical force, so that when this beam starts moving, it's not just the mechanical force that's moving it. There's also this electrical force that's being applied to it that's in phase with the mechanical motion. Anytime you have a force in phase with mechanical motion, that's a stiffness. Okay? And it turns out this is a negative stiffness. Okay? And that's kind of an interesting thing because there's a lot of EEs right now for energy purposes trying to implement negative capacitors. Turns out that this negative stiffness is equal to a negative capacitor. So in a MEMS technology, we already have a negative capacitor that can be used to interesting effects in actual circuits. And one effect you're seeing right here is that negative stiffness is subtracting from the mechanical stiffness, and it's taking us from this 10.4 megahertz to what we actually measure, which is 8.5 megahertz. Okay? So lots of things going into determining the frequency of this beam. A lot of things coming together. That's why it's micro-electromechanical systems. It's not just micro-mechanical systems. The electrodes in there, because both of these domains have to be accounted for to figure out what this beam is doing. All right, so this is interesting here. I guess I will label a couple more things because you'll see them a little later on in the course. This quantity right here, which is Young's modulus divided by density, the square root, this actually has dimensions of velocity. So it's meters per second is what you end up with. And so that's why this quantity is often called the acoustic velocity. Okay, and it turns out that this acoustic velocity is very much akin to the characteristic impedance in a transmission line. Okay, they're sort of the same concept here. And in fact, in mechanics, you can make a mechanical transmission line that's in many ways equal to an electrical transmission line. So you have transmission lines in mechanics as well. You're beginning to see the picture. If you wanted to make any circuit function, any transfer function, you can do it mechanically. The same way you can do it with transmission lines, transistors, resistors, capacitors, inductors. All of those elements are included in this mechanical field. Okay? And that's how we do signal processing with mechanics. We take mechanics, we equate it to an electrical equivalent, but the mechanics have desirable properties. You already learned that Q is much higher in a mechanical system. Okay, so what does that mean? That means if you can make a fully mechanical radio, which is the subject of some research going on even here at UC Berkeley, you can eliminate all the power consumption of your radio, at least the front end. So you have a radio that consumes zero power if you can implement all of the front end stuff mechanically. Okay, that's a very difficult thing to do, though, so it's very blue sky research. Okay, but theoretically it should be possible, especially after what you learn in this class. A couple other things I'll mention about this. You could see right away from the equation here, okay, I guess the equation's here. Right away from this equation, I can point out one thing, and that's that as L goes down, that frequency increases in a big way, right? Because this is now L squared that this is dependent on. Okay, and we could start thinking of how we can scale this whole thing. So let's now take a look at this equation and just talk about scaling. So there's a couple different cases that we can think of with scaling. So we can scale everything, right? Just uniform scaling. And so that means scaling all dimensions equally by some factor S. So case one, scale all dimensions equally by a factor S. Okay, where S, right, may take on 2 times if you make things bigger, half times if you want to make it smaller. Okay? And so how does that change the frequency? Where all you do is you take the frequency equation, which you see on this side right here, and you plug in S for any dimension that you're scaling. So I plug in an S for my H. So this is going to go as S in the numerator. I plug in S for my L, so S squared. So this ends up being 1 over S. Okay, so that means that if I scale this by 1/2 times, okay, then the frequency will increase by 2 times. If I scale H with L. Okay, but I can make a lot of choices. Right? I could make a second choice, and I can say, I want to scale L only and not scale H. So if I do that, then I can write an equation F naught then goes as 1 over S squared, okay, which is a much faster rate of increase for frequency. So, in the end, if I want a faster rise in frequency, I want to scale only L, okay? And that's the best way to do it, but right, nothing comes for free. If you do that, you're going to run into problems. Okay, we'll talk about that in just a second. But before doing that, let's put one more example down here. I'll keep that equation up on that side here. And basically, I want to find out what it takes to get to a gigahertz. I guess I'll just tell you right now. What it takes to get to a gigahertz is to make your length not 40 microns, but 4 microns. So if you scale that length by 10 times down to 4 microns, keep all the other dimensions the same way, and ignore width effects. Okay, so we're going to ignore width effects here. For now. And I guess I should tell you this is a questionable thing to do. I'm doing it now only because it's a simple thing. Later on, we'll get a much more accurate equation for this. Okay? But if we do this, we can then just plug into our frequency equation. This becomes 1.03 times this acoustic velocity, which I'll now give as 8,076 meters per second, times thickness, 2 microns, divided by now 4 microns in length. And that ends up being a frequency of 1.04 gigahertz. Okay? So you can see right away that dimensionally, 4 microns, that's a very manufacturable dimension using today's fabrication technologies, right? You know that you have transistors now that are down to 24 nanometers or so, right? This is 4 microns, right? That's 4,000 nanometers. It's many times larger than the smallest sizes we can already get in transistors. So this is not difficult to do. And so interestingly enough, in 1994, when I graduated with a PhD, there were a lot of people who didn't believe mechanics can go faster than kilohertz. Okay, I guess by that time they didn't believe mechanics can go faster than 20 megahertz. There were faculty at Berkeley, in fact, in the EE department who were basically telling us that okay, 20 megahertz is going to be your limit. Okay? But no, completely wrong. And so what that sort of tells you, you should trust theory. Right? If theory says it's going to be possible, it probably is. Okay? At the same time, I want to tell you not to trust theory, too. I'll tell you that later on. But at least for now, trust theory. Yes?
So what's the benefit of the increase to gigahertz instead of 10?
A gigahertz is where most wireless is. So your phone, for example, if you have a CDMA phone, it's either working at 900 megahertz or it's working at 1.9 gigahertz, somewhere around there, right? PCS, that sort of thing. If you're working, GSM is at, what is it? 1.8 gigahertz, right? And 900 megahertz. And so these are the frequencies that cell phones operate at. That's why you want resonators that can operate at those frequencies and select those frequencies. Okay? Yes?
So a couple things. First is the equation you get for the clamp standard.
Yeah, so I'm not showing you all of those different things. There are multiple modes, and in this case, a flexural mode is a dispersive mode. So it's not multiples. That's why I can't, if I were to write it down, I couldn't just put an I here in place of that 1. It's actually, they're not multiple, they're not harmonics. Well, I guess they are harmonics, but they're not multiples of another. Like your fundamental would be 10 megahertz, your second would be 24 megahertz or something like that, right? It changes with the mode. Yes?
That frequency equation, is that still valid for such a large aspect?
No, it's not. That's why I wrote this questionable thing to do. Okay, because when your width, right, is that much larger, actually your thickness too. So there's width, there's thickness, there's all sorts of different effects that go into this. The solution becomes much more difficult. And we've certainly worked it out, and there's papers out there that talk about the exact solution. But yeah, you would not end up with this dimension 1.04 gigahertz. So maybe just so no one is confused by that, it really is going to end up being maybe 800 megahertz or something like that. Right? Those effects will knock that frequency down, such that in order to get to gigahertz, you would really have to make that length even smaller, but still a reasonable length. Okay? And so at least in this case, things look good. But let me make some remarks now. Okay? I guess the first remark I'm going to make is the remark that sort of is what people have been asking. Okay? And so that's 1, that equation, which I'll call equation 1 now. We call that equation 1. So equation 1 is not accurate when L is about equal to H. Okay? So that's definitely true. Now, number 2, when L is about equal to H, or I guess I could say when it isn't more than, say, 10 times H. Then you have another issue that comes in, and that is you get anchor loss problems. Okay, so what do I mean by an anchor loss problem? So if I go back to this beam, and the beam sort of looks like this. So here's what the MEMS version would look like. It's going to have some anchor like that. And on the other side, also an anchor like this, where it is attached to a substrate. So that's my substrate. This is my beam in cross-section. That's an anchor. Okay, so what's happening as this thing vibrates? Well, this thing, right, you know that it's going to contort like this, but to contort like this is a significant amount of force that's being applied to it, right? Someone's applying a force in that direction. Okay, but if that's the case, then this beam is also lifting off the substrate with that force. The substrate has to fight back with an equal and opposite force to keep this beam where it is. So the substrate will fight back. And what that's going to do is that's going to radiate energy into the substrate. Okay, that is an anchor loss mechanism. Okay, and anytime you have loss, right, Q is equal to energy per cycle divided by energy loss per cycle. Right? This energy loss per cycle is going to go up, so Q is going to go down. And so that's the problem with just scaling one dimension. You can't do this. Well, you can, you're just going to lose all your Q. And so people have done it, we've done it, and we've lost all of our Q. So you start with Qs in the order of 8,000, 10,000 or so, you keep shrinking this down. By the time you get to just 100 megahertz or 70 megahertz, your Q has already gone from 8,000 to 300. Okay, it's that steep of a drop-off there. It's still a pretty respectable Q, from on-chip purposes, but not as much as we would like to have to create true revolution in some of these wireless circuits. Okay, so what are some of the solutions to this? So this is an example here, right, of one of the cons of scaling. Right? So scaling the length down to 4 microns raised our frequency to 1 gigahertz, but now we lose all our Q. There's a trade-off going on there. And so the engineer, right, the MEMS engineer has to think, how am I going to solve that trade-off? Okay, I want to keep that frequency, but I do not want to lose that quality factor. And so there's a couple ways to solve this. And let me make that remark number 3. So coming from that, remark number 3 is the solution to this, or one of the solutions, and that is to use nano dimensions. Okay? Don't just scale L, scale H too. Okay? But if you scale H, right, to get to 1 gigahertz frequency, you got to scale L more than 4 microns. Right? It turns out that to get to gigahertz frequencies, you'll have to scale L to about 1 micron long, but the thickness of the beam is going to be on the order of 300 nanometers or something. Okay, so you're at the nanoscale, not quite nanoscale in length, it's still about 1 micron long. It's 1,000 nanometers if you want to call that nanoscale. But it turns out if you do that, you will get frequencies on the order of gigahertz, and you'll do it with respectable Q. Okay, so that's one way to do it. This is one good way. But nothing is perfect, right? When you make it too small, and so this means, make this clear. This means H is going to be about 300 nanometers. L is going to be about 1 micron. Okay? That's a pretty small device. Okay? And one of the problems that you run into when you make a device that small is that the power handling of the device goes down. Okay, so we're talking about a wireless application, right? In wireless communications, you're receiving a signal at your antenna, okay? And that signal that you receive at your antenna usually is a pretty small signal. So probably this nano resonator can handle that signal, okay? But the problem is there could be people around you transmitting much bigger signals. In fact, the wireless problem is that you're trying to receive a signal from a faraway cell tower. It could be a mile away. Whereas your buddy is sitting there with his or her cell phone and transmitting right there 2 feet away from you. Okay, so your phone has to reject that transmission 2 feet away from you, which is going to be maybe 80 dB stronger than the signal you're trying to pick up. That 80 dB signal hitting your antenna and then hitting this tiny nano mechanical device, I don't know if it'll blow it out, but it'll create nonlinearities that will corrupt your whole ability to receive the faraway signal. Okay? So the problem with this is power handling goes down when size goes down. I mean, the smaller you are, the less power you can handle. All right? So there has to be a better way to solve this problem, and in fact there is. And so the better solution is to just be more creative about how you're making these resonators, okay? So abandon the guitar string and use other geometries, okay? And I'll put 2 check marks next to other geometries because that's a much better solution. So what do I mean by other geometries? So if I go back and I take a look at our problem, the fundamental problem here is that we're anchored at 2 locations as this beam is trying to contort up and down. Okay, so the problem is the anchors. The solution is to get rid of the anchors. Okay, and so how do you do that? You choose a mode shape. You could keep the beam, except use what's called a free beam. So one solution is to use a free beam. So what does that mean? This is a clamped beam. Okay, it's got fixed boundary conditions here. A free beam is a beam that is not held up by anything. So it's pretty much levitated. Okay? You might ask me, how do you levitate a beam? Well, we'll talk about that later on. You don't really levitate it. You just support it in such a way that the supports look like nothing. They're physically there, but as far as the beam is concerned, it sees nothing. And that's all in the mechanical circuit design. Okay, but effectively in a free beam, you're going to get a beam to contort in resonance like this, where its ends you can see are moving quite a bit. Right? These ends are really moving. Okay? And this part here is also really moving up. So the ends are moving down, the middle's moving up. Well, there's going to be some locations right here and here where there is no transverse motion. Okay, so these are nodes. Where the transverse motion, which means motion in the up and down direction for this, equals 0. Okay? And so basically put your anchors here. And you lose very little energy. Putting your anchors there makes your energy losses go away. Yes?
What's the advantage of that design compared to just a single support in the middle?
Single support, it depends on how your beams flap on those, because if the beams are flapping both directions at the same time, then you're going to be pumping your substrate still. But if the beams are doing this, then it's slightly better, but you still will get some rocking motion into the substrate. In this case, there's actually still rocking motion happening in the supports. So this actual design looks like this from a top view. Okay, you're sort of holding it up that way. And so there's no motion going up and down, but these things are going into torsion here. You still get torsional motion of those supports, and you have to design against energy losses. Turns out the energy loss design is simple transmission design, transmission line design. All EEs know how to do that. Maybe some MEs do, right? But it's a mechanical transmission line. You design it to be quarter wavelength. You knock out all the energy losses to the substrate. Okay, so there's where circuit design really helps this thing here. Okay, this is one design that can make it up to gigahertz frequencies and does a very good job of it. Okay, you could make your length smaller without worrying too much about making nano dimensions. You can keep your power handling high enough for practical applications. But this, in fact, is not the best design. And so that's the beauty of mechanics as well. There's tons of flexibility, right? I mean, think of this. This is the same problem as loss in an inductor, right? So for a transistor designer, you have an inductor. Okay? The inductor suffers quite a bit, not only from losses in its turns, but also from losses because there's magnetic coupling to the substrate. And the magnetic coupling to the substrate creates eddy currents in the substrate. Those eddy currents have to go through resistance, and so there's loss. Okay? What can you do to solve that problem in a circuit, in a transistor electronic domain? Not much. Right? You could use exotic technologies to lift that inductor above the substrate as much as you can. You can use exotic technologies, actually MEMS technologies, to turn that inductor around so its magnetic fields go this way and not into the substrate. Those actually work to increase Q to levels on the order of 40 to 80. Okay? But there's nothing like this, where you basically say, okay, I have anchor radiation. That is a substrate loss mechanism. Just eliminate the anchor radiation by eliminating the anchors. Right? The fact in mechanics you have so much design flexibility, you can do that. The other solution to this, and the solution that is probably going to be used most at gigahertz frequencies, is to really change that geometry. Use a radial mode disk. So now your resonator looks like this, and it's held up by a stem over your substrate. And the way that this actually vibrates is it expands and contracts along its circumference, sort of like a breathing mode. So if you make a disk like this that goes in a breathing mode, this point where it's anchored is a node. Okay, and it turns out this geometry is an extensional-like geometry such that you can have some very large sizes and still get to gigahertz frequencies. Okay, so this actually is the best design, I would say, to get to gigahertz type frequencies. Designs like this. And so far, incredible Qs have been obtained for this. So, for example, at 500 megahertz, Qs have been measured around 109,000 for this type of device. And with that kind of Q, you could do some really revolutionary things in communications and timing and all sorts of sensors, all sorts of things. Okay, so that, just an example of all the design flexibility we have here. Okay, now, beyond all of this, so this is all pretty cool right here. We're showing that scaling allows you to get to previously unachievable numbers. But it goes even beyond this. Scaling also, yes?
How's that actuated?
This is actuated also by electrodes along the edges. I'm about to show you some slides of this after I cover this next part here. But this is all really neat. But even neater than this is that these devices are tiny. So you're not limited to just one of these or a few of these. You can put thousands of these over a substrate. And if you can put thousands of these over a substrate, you can combine them into big circuits the same way that we combine transistors and resistors, inductors into big circuits that give us functionalities that the single device could not possibly give us. Okay? But how do we do this with transistors? Okay, so let's talk about circuits. For a second. Okay, so in circuit design, let's start with what we understand already, or what some of us understand already. So just transistor circuits. Okay, how do we do a transistor circuit? So in a transistor circuit, we have our, for example, an MOS transistor device. This is really what? This is really a physical device. Right? If it's an NMOS device, I'm going to have some source and drain, and some gate terminal and some substrate here. All in silicon, right? It's really a physical device. We give it this symbol right here, drain, source, gate. I guess I can even put the bulk in here too, right? There's our transistor. How do we make circuits out of transistors? We don't make them by just putting them together. We have to model this thing. Right? And so, for example, if we're making an analog type circuit, the model for this transistor looks something like this. Where I won't put all the details of this thing in. So that's our transistor. That's pretty much it. Right? And we repeat this again and again. Very simple model. We repeat that model again and again for each transistor that's in the circuit. And we use simulation programs like SPICE to help us to get very accurate measures or predictions of how the circuit will perform. Okay? So we're using this equivalent circuit for the transistor. Exact same idea in the mechanical domain. Okay, it's really no different. So if we want to talk about a mechanical circuit, we're now looking at a different looking thing. Right? It may be this beam, okay, that has these anchors at the end. Okay, where that's the anchor there. Okay, maybe I have an electrode like I have in those previous circuits like this, that can electrically excite this thing. So the way that you would normally excite this is you would put some kind of DC bias voltage here. And then you would put your AC excitation voltage right here. That's your AC voltage, VI, coming in there. And you may detect an output current coming out of this. Okay? That's the device. It has a physical implementation right here, just like the transistor has a physical implementation. Okay? And it also has an equivalent circuit. And the equivalent circuit for this mechanical device happens to look like this. Okay? Similar sorts of things, but also some differences, right? You have transformers in the technology. You have a resonant tank circuit here that obviously you know would be needed. And so all of these things come together right? So this is your equivalent mechanical circuit. So think of this as just being some other physical piece of thing, right? Just like that's a physical thing. It's a thing, right, that we're equating to a circuit. This is a thing that we're equating to another circuit. And now we can take that circuit, put them into much larger networks of mechanical parts to create a much bigger network that has a function that is much greater than the function of the single device. Okay? So we're doing exactly the same thing as transistor level design, except we're using mechanical parts to do that, with advantages in some cases, with disadvantage in other cases. So in the end, you probably want something that marries the transistors together with the mechanics. Okay? And that's a lot of what MEMS is about as well. Okay, so that's, I guess, taking a look at vibrating RF MEMS there. Let me go back to this mode here, where we've already sort of gone through that. And just keep going with this. So this is an example of a mechanical circuit that I've been talking about. All right, so you see a beam right here, which is equivalent to that beam that we just saw. In fact, this is exactly that beam. Okay, but there's not just one of them, there are three of them here. And you're taking these three beams, each of them has its own electrode, you could see, going underneath it. Okay, and you're connecting these beams. These beams are connected to one another. These beams, which are non-adjacent, are connected to one another. This creates a circuit, a mechanical circuit that now gives you this transfer function, okay, which if you zoom in on this at lower powers, looks like a filter transfer function, right? This was attempting to be a Chebyshev type filter. It even has sort of a loss pole here, which was also attempted on this. But in the end, it's the lateral dimensions of all of these things that specified an equivalent circuit that gives you a filter. And in fact, you can really call this an electronic circuit by just equating all of these things. Okay, so if I look at this thing, I can make some equations. I can equate some things right now very quickly. So each of these beams, right, just the beam itself, this is the resonant beam. That's the same thing as an LCR circuit. Okay? These beams right here are kind of interesting, right? They're actually sized in length, or length, width, and thickness, to be a transmission line. Okay, so this is a transmission line. This actually has that equivalent circuit. That's the equivalent circuit for a transmission line, which usually you see as two inductors and a shunt capacitor. But in this case, this is a quarter wavelength one, so we're showing it as all capacitors, where the capacitors have positive and negative values and they cancel each other out to do the quarter wave thing for transmission lines. Okay, even the input-output, you're going from mechanical to electrical here. That's also implemented by a transformer. And the places, what did I say? These are transmission lines, not transformers. Did I call these transformers or transmission lines? I did say transmission, that's good, okay. But these are transformers here. But not only that, where you attach these to the beams, right? I could have attached this right here, or I could have attached it here or there. Where I attach that to the beam, does a velocity transformation. And so that attachment point actually implements this, okay, which is a transformer. So in this mechanical technology, you've got inductors, you've got capacitors, you've got resistors, you've got transformers, right? And transformers are something you do not have in conventional IC technologies as well, right? It's difficult to get a transformer. So there's a lot more you can design here just in this mechanical technology. And if you combine this then with transistors, you have a sea of flexibility in what types of design you can do. Whoops. Okay, so this is an example of that disk resonator that I talked about. Let me move this back to this. Okay, so you can see this is the disk. This is the stem. This is the stem that goes through the disk and actually attaches it to the substrate. These are the electrodes surrounding the disk. You can see the gaps between these electrodes and the sides of the disk, but those gaps are on the order of 80 nanometers. So they're very small gaps. You want that gap to be small so the electrical force can be very large to drive this structure. When you put an electrical signal that's at the resonant frequency of this thing, it will vibrate in this mode shape. So here's an actual example of the mode shape. So you can see the electrodes surrounding this. You can see that mode shape. You can see that gap changing with that. As that gap changes, it's going to change the current that's flowing between this. So the current flows because of the motion. If there's no motion, there's no current flow. But as soon as you move, you get current flow. You pick up that current flow as the output of this device. And you could see that for a 20 micron diameter, at least for its second mode of vibration, this is at 1.5 gigahertz. And it's got a Q of 11,000 in vacuum. And the other thing that I can say is the Q in air is 10,000. Okay, so remember with that beam that we had before, that when we put it in air, its Q dropped to about 50? Not happening with this device. And it's not happening with this device. I think this was a big deal when we first demonstrated it. So this was the slide that did it, right? This was shocking to a lot of people, right? MEMS was pretty much relegated to, you better have an expensive package or else, right? This removed that. And the reason why this is happening is because there's a lot more energy in this device. It's a much stiffer device. Okay, so the stiffness, for example, in an accelerometer is on the order of 1 Newton per meter. The stiffness of that beam that I showed you at 10 megahertz is on the order of 1,000 newtons per meter. The stiffness of this is on the order of 50 million newtons per meter. Okay, what is energy? 1/2 stiffness times displacement squared. Okay, you have a large stiffness, you have a lot of energy. So it has a lot of energy with which now to push the air molecules around. Okay, it's even more interesting than this because it's even more like integrated circuits, electronic circuits, in that when you go to higher frequencies in a circuit, what becomes more important? Does resistance become important, or does capacitance become important, and inductance, right? When you go to higher frequencies, suddenly those resistors are no longer there, and it's all capacitors and inductors. What does that mean? That means your signals are going through the capacitors and inductors, which are lossless elements. You have less loss. That's also happening here as well. So what's the gas damping, which is a resistive damping method, is going away at the higher frequencies as well. So you've got two mechanisms that allow this to reach the Q of 10,000 in air. Is that a question?
Does this mean that this design consumes more power?
No.
More energy?
So it has more energy in it while it's vibrating, but it doesn't mean it's consuming more power, because the way that you put energy in, with high Q resonant circuits, what's really happening is you may have a tiny little bit of energy you're putting in per cycle. So you put that energy in per cycle, but you never lose it because the Q is so high. So what happens is you don't immediately get that energy. It takes time to build up that energy. But once you build up that energy, you're losing so much energy per cycle that it's all contained in there. And so I guess the difference between a high Q, like a guitar string, a high Q guitar string will last a lot longer than a low Q guitar string. Right? If I have a Q of just 10, it's going to last, maybe 1 second. Less than that, actually. If I have a Q of 700, it will last, 10 seconds, 20 seconds or so. In fact, that's exactly what an oscillator is. So if you do oscillator design, oscillators in their positive feedback loops actually kick the Q up to 10 to the 11th, 10 to the 15th. So you actually have such a high Q circuit that its time constant is so long that the oscillator stays, it's what you see as an oscillator, very stable frequency. Okay, that may be over, beyond some of what you recognize, but just the high Q here doesn't mean and a lot of energy. If it has high Q, it can have a lot of energy without you needing to consume a lot of power to give it a lot of energy. Okay? All right, so this is an example of an even bigger mechanical circuit. This is also a mechanical filter. I won't go through this. I'm just showing this to show you how complicated these things can get. And so then where can you use these things? Well, I was talking about wireless communications, right? So in wireless communications, you usually have some very complicated circuit that implements your phone function. Okay, so you see your antenna receives the signal. You go into maybe a diplexer, which is a switch that switches you from receive to transmit. We're just looking at the receive path right here. This is the first thing in the receive path you can see is a filter. Okay, and why that filter is there, it's there to knock out those interfering signals so that you only see the signal you want. Only the signal you want, plus a few other signals that this circuit can handle, are received by this circuit. Because these transistor circuits, they have a limited, what's called a dynamic range. Okay, if you give them too much signal, they won't be able to decipher the small signal you're looking for. All right, and so you need this filter in order for this to work, and this filter might be implementable using this MEMS technology. Okay, in fact, it is implemented right now using a different kind of MEMS technology, which is what the F-bar is. It's a thin film bulk acoustic resonator. And all of your cell phones, well, at least your CDMA cell phones, have this. Okay, your GSM cell phones use what's called surface acoustic wave resonators, which just by the word acoustic you could tell is pretty much a MEMS technology too. Right? And the inventor of the SAW is in this department. This is Professor Dick White, actually, who's retired emeritus, but he invented the SAW resonator that's basically being used in every GSM phone that's out there. Okay, so if your phone does GSM, if you're on AT&T's network, you are using one of his SAW resonators. If you're on Verizon, which is CDMA, you're using the F-bar type stuff. But this is where you might be able to use this technology. I guess in the end, why is this so interesting? It's interesting because even though you see just a few of these orange things, which are the off-chip components, they actually take up a good portion of the size of your cell phone and a good portion of the cost. All right, so if you look at this cell phone here, if you open up a cell phone, look at its RF portion, you'll see something like this, where you can pick out a number of these surface acoustic wave filters in this case. These are those macroscopic filters. You can see how big they are on the board. You can pick up your crystal oscillator, which is also using a mechanical element to get very high Q, very stable frequency. And then here are your electronics. Well, not yet. There's a diplexer, your switch. And so here are your electronics. There's your power amplifier. This is a 0 IF dual band demodulation chip. And this is your VCO right here. And all the rest of this stuff here are inductors, capacitors, resistors for biasing. And you can see that it's the passive devices on this that are the bottleneck to miniaturization. Okay, these transistor circuits are getting cheaper and cheaper with time. Right? They're becoming commodities. It's these other things that are not transistors that cannot be miniaturized yet that are costing money in cell phones. This is a dual band phone. You can look at it, right? That's a pretty old looking phone, isn't it? No, none of you guys have the, well, I don't know, you're students, so maybe you don't have some of the, well, you probably all do, have the latest and greatest in phone generations. If you have one of those handset devices that like a Galaxy phone or iPod and that, or iPhone and that sort of thing, those things have lots of filters in them. Okay, so you're looking now at 20 filters or so in your average phone like that, if it's a world phone. And the number of filters is just going to increase. The number of these off-chip components is just going to increase as you want to do more things with your phone, right? So in the past, right, it's always voice. Now you're picking up TV signals. Soon you'll be able to operate your vending machine with your phone, or maybe you can already do that. Right? Soon you walk into a room with your phone and your TV turns on. Everything, your lights turn on. Maybe your dog gets your slippers for you or something. I mean, automatic things start happening with the sensor network, and as the sensor network gets bigger, unless there's some way to solve this dynamic range problem, there's going to be more of these filters. Okay, and so that's why your new architectures may look like something with this, with more filters. And the way to implement an architecture like this is not to keep buying every SAW filter for 10 cents a piece. Right? If you need 100 SAW filters 3 years from now, that's going to cost you $10. Right? But if you can use a MEMS technology or a similar technology like this to put all those filters into a single chip that costs 10 cents, yet still sell that for $10 or make it $9.99, right? You'll make a killing, right? So that's why there's a lot of research. This is an example of one of these chips that can put all these different filters on just a quarter of a millimeter by half a millimeter. That's what could be possible to get all of that. And so that's why there's a lot of thrust into this kind of MEMS technology. One great example, I think, of how shrinking dimensions allows you to really do a paradigm shift in what can be done. Whoa, it's already 3:34. And what can be done in wireless communications. So the next thing I'm going to talk about next time is atomic clocks, which is another very interesting thing